Let's start the second part of today's lecture. Now that we learned how to encode recursion without using recursion, let's see what we discussed is, generalizable or not. So implementing recursion could be using recursion or without using recursion, meaning that when we define a recursive function factorial, we may want to use the recursive keyword DEF. But just using this recursive keyword does not teach us anything about recursion. So in order to understand what's going on behind the curtain, we may want to implement recursion without using this recursion keyword, meaning that just using this eval keyword and lots of function expressions and function calls. You saw many of that before the break, right? So define this mkreg as a library function. We did not need to use recursion. Wow, but that was crazy. So in general, when we have this DEF keyword to define recursive function, the recursive function name id1 and the parameter name id2, and then this function expression, that's gonna be the recursive function definition. And we can use this name id1 in both expr1 and expr2 because it's recursive. And this could be parsed the same as this way, meaning that these two mean the same thing. Instead of using the EF keyword, we can use val keyword and defining this recursive function. But note that this mkreg library function is unique, and it expects that its argument expression should be function expression where the parameter name should be the same with this recursive function. Then you can use this name in the function body. That's the trick. Okay, if you don't see it, if you don't get it, go back to the first part of today's lecture. Then you can use this trick, and then remember, we do not need this val thingy because we have function expressions and function calls. So this one is just the same with what? Yeah, this recursive function name id1 is that thing. This is the argument bound to this recursive function. Make a recursive function by using mkreg library using this function expression whose parameter name should be the name of the recursive function, those two. Then we can use this trick. Wow. It works. It's interesting, but it's crazy. You may not want to use that trick. So let's see another approach, which is not that pretty or mathematical as before, but way more simpler to understand. Let's see. But in order to use this simpler simulation, now we need to dirty our hands by using mutation. var instead of val. Instead of val, we are going to use var, and we are going to make a name fake first and initialize that with a garbage value 42 in the beginning, and then change the value with the real function value. Oh, do you see that? Yeah, do you see it? That's the trick. In the beginning, we say that I'm gonna introduce a name fact. That's something. I don't care about its value in the beginning, so give it whatever value. 42? Yeah, whatever value you want, because it's gonna go away, because right after introduction of the name, you're gonna replace that with this expression, function expression. In this function expression, we have fact. Wow, that's gonna be this name, but its value is not 42 when we call it. That's the trick. How come does it happen? Let's see what happens. So implementing recursion may need to use recursion. Again, that's going to be simple, but you are not going to learn anything about recursion. So we are trying to implement recursion without using recursion, without using the recursion keyword DEF. Then what? Either using the function applications and function expressions a lot, like the crazy mkreg trick, or use the var approach. The var approach to definition works only when the defined language includes var, meaning that if you want to use this var approach in RFAE, we need var in RFAE. We need var in this RFAE, but we don't need it if we implement that in Scala. But the var approach to implementation requires only that the implementation language Scala includes var. Let me explain what I meant. So let's go back to this RFAE language, the usual thing, and the recursion, and then if0 expression. We are going to implement this semantics in Scala. So let's revise that expert. Now we are going to have if0 conditional expression, true expression, false expression, right? Recursive function, function name, parameter name, body expression, which should be function expression, right? And the parameters body expression, and then expression to use this recursive function. Okay, then let's see. Now we are changing the value for recursion. Again, value has two variants, number and closure. Num_v has a number, closure v has a parameter, which is a string, body, which is an expression, and environment, which is an environment, a map from names to values. But now the env has this var modifier. Ooh, we told you not to use var as much as possible, but now we are using var. Yeah, to implement recursion, we had to dirt our hands. Let's see why we had to use this var modifier for the environment. This is the usual interpreter. Let's implement the simple case first. If0, what's the semantics? What's the semantics of if0? And what are they? If0 has three expressions. The first expression is for condition. The second expression is for true branch. The third expression is for false branch. So we are gonna interpret the first sub-expression, C, conditional expression. When its value is 0, then we are gonna evaluate the second sub-expression. If the value of C is not 0, meaning closure v as well, right? It's not an error here. If the value is not 0, then we are going to evaluate the third sub-expression like this. Interpret the first sub-expression depending on its value. If its value is 0, num_v and the number itself is 0, we are going to interpret the second sub-expression. Otherwise, meaning num_v and where n is not 0, or what closure v right? So when we have if0, e1, e2, else e3, here, when e's value is not 0, then even though it's not a number, we are going to evaluate E3. That's the semantics. Later, after the midterm exam, and when we learn types, we may want to reject such a case. When we have a typed, well-disciplined language. Until then, we are going to just allow that. And when the value of C is non-zero, then we are going to just interpret the third expression. So far, so good? What's recursion? Yes. What is recursion? Okay. Recursion, REC, takes 4 arguments, 4 fields. F for recursive function name, X for the parameter name, B for expression, and the function expression, body expression, and E is the use case. Let's see what happens. So we are introducing a name F. And we are also introducing another name X. And we know that the function's body is B. And using all that information, we are going to interpret E, right? Okay, so we are making a closure V. because it's a recursive function. What is closure V? How do you make it? Oh yeah, you know what? Closure V takes 3 pieces of information: parameter name, body expression, and an environment. Which environment? When the function was being defined. Oh, right, we knew that. So when this function is being defined, we have this environment. So let's make it. Closure V, parameter name, body expression, and the environment when this function is being defined. Are we good? Is there anything for us to do more? What do you think? Are we done implementing this semantics? If so, recursion is not that complex, right? What's wrong with this implementation so far? Is this clear V the semantics of this recursive function? You think? If so, it's just like what? Val f equals x arrow b, like that. It's just like that. But we should make it a different thing. How? Because this f should be available in here with DEF, with recursion. How can it make this f available in this environment? The current environment, you see that it does not have the information about f. Okay, let's add it then. We are gonna add this information saying that f's value is closure V. The closure V that we just made here. Okay? Add that to EMV, the EMV that we received, the environment that this recursive function is being constructed. And we're gonna call that an EMV. Are we done? Not really. One more thing to do. Now that we have this new environment, which has all that in this environment, in this given environment, and the information of the recursive function, we need to change the inv component of this clov with this new one. Ooh, are you with me? Are you following? Right? And then using that information, we can interpret the real expression. One more time, the concrete syntax is what? DEF, yeah. I'm going to define a new function f whose parameter is x and the body is b. Using that definition, we are going to evaluate this expression. That's this recursive function of f with parameter name, body expression, and the expression that's going to use this function f. Actually, this e may not use this recursive function. It's okay. You just wasted your time by defining this function that is not going to be used in e, but there is no harm. 시간만 버렸지만 상관없어요. But when we use it, another thing. This is a recursive function and this f may not be used in function body. Well, it's not a recursive function, but you just defined it. It's no harm there. There's no harm. But still, in general, f is available in B and E. So when we evaluate this E, we may call f, then we are gonna interpret this function body B, and when we interpret B, we may need to look at this f, and f should be in the environment. So when we interpret this expression E, we need an environment that has every information available here. On top of that, the value of f. So this NEMV is what? On top of this given environment, we added this information saying the recursive function f's value is closure V. And closure V is again parameter name, body expression, and the old information here, but we replaced that with this new environment right there. Do you see it? That's why we needed var here. In the beginning, we created closure V with a wrong value for EMV, right? Why? Because we started with this EMV that's given, wrong environment, and then just make a wrong closure V to have that and change it the real component with the value. Okay? So you should be able to explain the semantics of that. And to help you, we are gonna have an example run and try to see what we just implemented means. Okay, are you ready? One more time. This one, you should be able to explain what you are supposed to do when you interpret this. When we say run this thingy, what is that? It's an expression. It's a function call with this function definition. This definition is defining a recursive function count whose parameter name is n and body expression is all that. It actually calls its recursive function here, and we are going to use that. We are going to call it using the argument 8. How are we supposed to call this? How are we supposed to interpret this? Yeah, look at that. This inter function takes an AST and an environment. In the beginning, the environment has nothing. It's the usual empty blue box. And in the beginning, the entire code is going to be evaluated. And the entire code is recursive function. We have recursive function, count, parameter name, and body expression if 0. And using that information, we're going to call this count 8. Right? Are you with me? Then what's next? Let's see what I just said is correct. Yeah, the recursive function name is count, the parameter name is n, and the body expression is if 0. Actually, we need an AST, but it's too long and tedious. Let's just use this parser call. Okay, that's the body. And what are we supposed to do with that information? We are gonna call count function with argument 8. In the beginning, environment is empty. Nothing surprising, right? Okay, when we have all that, when we have all this, what are we supposed to do? What we are supposed to do in the beginning is to create closure V. Create closure V with parameter name, body expression, and environment. Okay, let's create closure V with parameter name, body expression, and the environment. What's next? Oh yeah, the next thing to do is to construct an EMV, new environment, which is gonna extend this environment, the old environment, with this information. The function name has this closure V. Oh, really? Okay, that's easy. We can do that here. New environment is an addition, but the old environment is empty, so we just add one piece of information saying that this recursive function count has value clovy, this one. Let's use a pointer to say that because we don't want to write that all the time. Okay, then what's next? The next thing to do is what? Now that we have clovy, now that we have new environment, let's replace this wrong environment, the wrong environment that we had in the beginning, with the new one. Let's get rid of this wrong one with a correct one. So we are going to get rid of this old information, this wrong environment, with this new environment, like that. So now clovy is a closure V with the parameter name, body expression, and this correct environment. Then what are we going to do? The next thing is the interpretation of this expression. What is that expression? Function call. Then we need code for the function call, right? Okay, so what is that again? That's interpretation of function call. And then the environment was what? Yeah, this one, the recursive function. Its value is clovy. The recursive function count, its value is clovy. Okay, very good. Right? Then what's next to do? The next thing to do? Because it's function call, we need to interpret the first sub-expression, and then we need to interpret the second sub-expression. Okay, then let's do that. we are going to interpret the first sub-expression whose value is what? F. Okay, we are going to interpret F, which is count. It's a name, so we need to look up the environment. Its value is Clovey. Okay, good. Let's interpret the second argument, which is 8. Do you know how to interpret 8? Yeah, that's number, right? So it's gonna be num V8. Are you with me? Okay, that's good. Then what's next? Then we interpreted this one and we got Clovey where parameter is n, body is BB meaning this if zero thingy, and then FEMV is what? FEMV? Yeah, this one. FEMV was this one. Why? Because that's how we changed the environment. So in the environment, we have this count recursive function has the value Clovey. Right? Right. So then what do we do next? We need to interpret the body by extending this FEMV with the parameter name and has this in the value of the argument expression, which is num V8. Right? Yeah. Then what's going to be the new environment again? The new environment, FEMV has this information, and we extend the environment with this new piece of information. So the environment is going to be what again? Yeah. Count has Clovey and has num V8, and then we're gonna evaluate the body expression. What's the body expression again? If 0, and what's the value of n? Num V8. Is it 0? No, then let's do this. What's that? 1 plus recursive function call. Yeah? Just like the previous one, recursive function call. Okay, what is count? Look up the environment. It has Clovey, which is this one. What is n-1? Yeah, let's skip that boring part. It's gonna be num V7. Then using that information, we are gonna interpret body. This time, what's the value of count? The same Clovey. What's the value of the parameter this time? 7, num V7, like that. Here's how we can interpret this recursive function call by having this simple, how many lines? 4 lines of code. So one more time, when we have recursion of function named f with the parameter named x and function body expression is b, using the recursive function, we'd like to evaluate this expression e. The first thing to do is to make a fake wrong Clovey. Closure v with the correct parameter name, with the correct body expression, and the wrong environment. Why are we making this wrong environment? Because we don't have the correct one yet. But we do need a name for that. So we make this thingy just for now, and then make a real new environment, saying that on top of the given environment, recursive function's value is that closure v. It's not yet correct just yet, but it's going to be correct after this line, this blue mysterious secret line, saying that, hey, you, Clovey, I know you have this wrong information. This is the time to get rid of it and replace that with the correct one. Oh, where did you get it? Right here. Here we have a cycle even in the data structure, but we created that by using this variable, this mutation. Using this new information, now we can evaluate the expression. Do you see that? If you don't see it, just follow what I did. The important thing is that you need to do that by yourself. Don't just watch what I did multiple times. Do that by yourself.